Hi everyone, Mr. Smith here. In this video lesson, we are going to be talking about simple harmonic motion. Let's get started. What is simple harmonic motion? So simple harmonic motion is periodic vibratory motion in which the force and acceleration are directly proportional to displacement. So we're going to look at simple harmonic motion in the context of a mass on a spring. So maybe you guys, hopefully you did, played around with the PhET simulation, and when you hang a mass on a spring, it's going to bob up and down and bob it up and down. And the same thing would happen with a spring that's horizontal. If you compress it and put a mass on it, it's going to bob back and forth. Other examples of simple harmonic motion could be just like a pendulum and a clock swinging back and forth, or a bridge or building that's kind of like rotating due to the wind or something like that. But again, we're going to look at it in the context of a mass on a spring. Now I want to add one thing here too, is this definition works for springs because the force on a spring is directly proportional to displacement. So it's a natural fit for simple harmonic motion. And my hope is too that you checked out the crash course video. It has some great visuals and just kind of, it does explain a few of the things we'll be doing together, but especially for the derivation of the period of simple harmonic motion, I think having that visual is very useful. So I definitely encourage you to watch that. So what we've already talked about with respect to conservation of energy in an ideal spring is that we've talked about our spring energy or elastic potential energy being, spring energy is 1/2 kx squared. Now, as we think about how that energy is transformed as a spring moves, a mass on a spring moves back and forth and back and forth, hopefully you're convinced that when the spring is, say, compressed all the way. So here we use x equals a to say that's like the maximum or amplitude stretch or compression of our spring. When you compress it all the way, the stored energy is at a max, and initially the speed is 0. When you release that, the spring is going to go back and forth and back and forth, and it's going to go, after you compress it, it's going to go back the other way. And if you ignore friction, it's going to stretch to a maximum of a meters. And at that point too, the stored energy will be the same as when it was compressed, but at the same amount. And at that point where the mass is just going to turn around and go back the other way, every time we reach a turning point, the speed will be 0 and the kinetic energy will be 0. And you can see too that as the spring passes through that point where it's unstretched, there's no stretch or compression, all of that potential energy is going to be converted to kinetic energy. And that's where the spring will be moving the fastest. So that's the big idea for now for a mass on a spring, is that at the max compression or stretch, the amplitude, the stored potential energy, spring energy is a maximum, and the kinetic energy is a minimum. But when the stretch is 0, so when the elastic potential energy is a minimum, the kinetic energy is a maximum. And that's when your speed of your mass on the spring will be the fastest. In this system, the maximum potential energy would be something like this. ES max, I use S for spring energy. It's the same as EE. I might save EE later though when we do electric potential energy. But the maximum elastic potential energy would be 1/2 K, and the maximum value for X is the amplitude A. So we'll use that later. ES max is 1/2 Ka squared. That's the maximum energy stored in the system. So some key ideas that we've mentioned you may want to get down. The elastic potential energy is greatest at the 2 turning points, and there the speed and kinetic energy are momentarily 0. So we chatted about that. You might want to get that into your notes. And the kinetic energy is greatest when there's no stretch compression. So right in the middle of that simple harmonic motion. And again, you may want to get that into your notes. If you want to pause the video to get those down, that's fine. I'm going to move forward. So we talked about those in detail. All right. Interesting question is, so if I have a mass on a spring and I, pull it a certain distance and let it go back and forth, can I quantify how long it will take to go back and forth in terms of things like how big the mass is and how stiff the spring is? And we actually can. So that's actually pretty cool. And we're going to do that derivation together because it actually requires nothing more than some of our talk on spring energy and some uniform circular motion, actually, which is pretty interesting. It turns out the period of simple harmonic motion of a mass on a spring is given by this: 2 times pi times the root of the mass on the spring divided by the spring constant of the spring. And I'm going to show you guys why. And this is why watching the crash course video might be helpful, because they have this kind of same diagram, but it's actually in real time, so you can see it going. But imagine if you had just like a rotating disc and some handle pointing up, and that was to go round and round and round and round. But then you had a light source shining on that peg, and so the shadow maybe goes to the wall behind it. As that handle goes round and round and round, and you saw the shadow on the wall, what's actually really cool is that the motion of the shadow on the wall mimics exactly the motion of a mass on a spring, like exactly. And again, just a 2D image doesn't do that justice. You should definitely check out that visual in the crash course video. But yeah, as the handle goes round and round in uniform circular motion, that projection on the wall of the handle goes back and forth, mimicking a mass on the spring. So there's some connections to be made there. And so we're going to make them right now. And we're going to derive this expression for the period. So our starting point is the following. We know that on a mass on a spring, the maximum spring energy is going to correspond to the maximum kinetic energy. We just know that from conservation of energy. If you ignore friction, then no energy is going to be gained or lost. It's transferred from spring energy to kinetic energy. And so that's our starting point. And we had an expression for the maximum spring energy. It was 1/2 Ka squared. So A is the amplitude of our simple harmonic motion. And we'll do 1/2 mass for the mass in the spring, and we'll say V max squared. So a couple things, the 1/2s divide out. And if we rearrange this for V max, it's not too hard to do. We divide by M, and then we'll square root it. So we get an expression for the maximum speed of a mass on a spring in terms of the spring constant, how far you stretch it initially, and the mass on the spring. So now let's make a connection to uniform circular motion. So instead, now at that point where, say in the middle of the spring where x equals 0, the speed of the mass there, that maximum speed, is going to correspond to the speed of that uniform circular motion. And so we can also say that V max is the distance this handle travels around the disk, which would be its circumference, 2 pi r or 2 pi a, over the period, the time it takes for that handle to go all the way around. And if we equate 1 and 2 here, we get that 2 pi a over t equals the root of Ka squared over m. And we can make some simplifications here. So we have 2 pi a over t. If you look at the right-hand expression, notice how you have an a squared inside. Well, if you square root a squared, you get a. And so then we have a, and we still have the root of k over m inside the root. And now we have a factor of a on both sides, which is pretty cool. And we can solve for the period. So we have 2 pi over t equals root k over m. If we flip that, t over 2 pi equals the root of m over k, and we get what I mentioned earlier, that the period of simple harmonic motion is 2 pi times the root of m over k, which is really, really interesting that it doesn't involve the amplitude at all. So what that is saying is if you stretched a spring, really massive spring, really far and let it go, it's going to move back and forth very fast with a certain period. If you moved it back just a little bit, the motion will be slower and it's going to take the exact same amount of time. So you might have a smaller V max, but the period's the same. It's really cool. The period of that SHM is the same no matter how far you stretch it initially. So if the period is 1 second for a big stretch, it's 1 second for a small stretch too. It just moves slower. So that's very, very interesting. But yeah, that derivation isn't overwhelmingly complicated, and it ties in uniform circular motion. So I thought that's pretty cool to share with you guys instead of just dropping the formula on you. Let's keep moving. So let's do an example. Oh, that number got butchered as I was copying things over. But we have a mass on a spring, so 0.45 kilogram mass. Let me just consult my notes to see what that actually should be. 1.43 times 10 to the 2 is what that guy should be, or 143. So a spring constant of 143 newtons per meter. The mass spring system is placed horizontally, and the mass is on the surface, and we neglect friction here, so that the mass will just be bobbing back and forth, in theory, forever with no friction. We have the amplitude that we displace the mass 15 centimeters, and then it's going to be released. We're going to determine the period and frequency of the simple harmonic motion. So this 15 centimeters is a bit of a red herring because the period is independent of the stretch. So you actually don't need to know that it was displaced 15 centimeters. All you need to know is it was displaced. So the mass on the spring will bob back and forth. We have everything we need to calculate this period. So let's do it. Period is 2 pi times the root of m over k. So this is just a plug and play question, nothing too complicated. Plug in our mass, 0.45, and plug in k, 143. And then let's work it out. 2 times pi times the root of, I'm going to try to do this all at once. 0.45 divided by 143. Yep, I got about 0.35 seconds. And what this means is the frequency, and remember frequency is just 1 over the period. So 1 over 0.35. So that looks like to be about 3, 1 divided by that, I think. Yeah, about 2.9. So every second, this mass on a spring will do about 2.9 bobs back and forth, almost 3 full bobs back and forth per second. So again, that's just an easy example playing with the formula. Let's do some examples where we tie in conservation of energy. So we have a 3 kilogram mass attached to a horizontal spring, and we have the force constant of the spring, and we're told it's compressed and released from rest. Undergoes simple harmonic motion. In this case, the mass stays attached. And what we're told is, so we're not told the amplitude, we're just told that at a certain position, a certain stretch or compression, it just says 50 centimeters from the equilibrium. So that could be a stretch or compression, but it doesn't matter. We have a speed of 7.5 meters per second. So we're going to find how far the spring was compressed initially. Now, you can do springs vertically that involve gravitational potential energy, but we don't, and this is a horizontal spring. So hopefully you would agree that there's no change in gravitational potential energy for this problem, which is why I'm not including it here in my conservation of energy, because it would just be 0 for both cases anyway. So it is compressed and released from rest. So if it's released from rest, that means that initially V1 is 0, and that the initial kinetic energy is 0. And so we have 1 half K. And if you like to use A for since it's compressed initially, that's like finding A, you could do that. Or if you like to use, just like kind of keep it what we've been doing, if you want to use X1 for initial stretch, that works too. And then the final spring energy is 1/2 K X2 squared. So X2 is the final stretch plus 1/2 M V2 squared. So nice thing about this problem, no halves, the halves all divide out. And we have K, we have M, we have the final X2 and the final V2. So we can solve for X1. And I might do that just right now. So to get X1 by itself, we would divide by K. So you have KX2 squared plus MV2 squared. So divide by K, and that would give you X1 squared. We just have to square root it. So we've set it up. If you like to plug in your numbers and do that right away, that's good. Or you can solve in a general sense like me first. So what do we have? We have 85. Got to be careful. That is 85 newtons per meter. The 50 centimeter stretch we're given, we need to put that in meters, so 0.5 squared plus 3 kilogram mass, 7.5 squared, divided by the spring constant. So what we're expecting is we're expecting a larger stretch than 0.5 because it's the amplitude, right? So 85 times 0.5 squared plus 3 times 7.5 squared divided by 85 root. So I got about 1.5, which makes sense, should be larger. This is a pretty long mass on a spring, but that's okay. So about 1.5 meters is the initial stretch slash the amplitude. All right, so our first example of playing around with conservation of energy with something in simpler harmonic motion. Let's try another one. So let's find the maximum speed of the mass. So in this case, we're using a different position. So now, if I can maybe get let's go back to this visual. So in part A, we might have had information about maybe a point like this, right? With a certain stretch or compression, we found a certain speed. But now in this part B, we're looking at the maximum speed. And then if you want to think, what would the compression on the spring be when we have that maximum speed? It's 0. So if you want to actually draw a diagram like that for this question, you can. We're going to set it up in a very similar way. You have some choice here, actually. So you actually know two conditions now. You know the initial stretch and initial speed, 0 and 1.5 meters, which was a bit rounded. Or you know 7.5 meters per second and the 50 centimeter displacement. So I'm going to use, I didn't write this in before. I'm just going to write this in now. E before equals E after. And I'm going to use my before condition as the max displacement. And so that's I know that at that max displacement, that all of the energy is in spring energy. And then, and afterwards, that's when the stretch is 0 and our speed will be maxed out. So that would be maximum kinetic energy. So that's just how I'm choosing to set this one up. Again, we found the amplitude, right? It was about 1.5 meters. It's 1/2 mv max squared. But the big idea is we're just using conservation of energy. The spring energy, or the speed is the highest, is 0. And the kinetic energy at that max displacement is 0. I like using these two because the more things that are 0, the better. We could have also used, if we used the other condition where we had a little bit of spring energy and a little bit of kinetic energy, like there's nothing wrong with mv max. There's nothing wrong with that, right? And using this speed and this displacement, we get the same answer. In my opinion, though, when more things are 0, we just get things done a bit more efficiently and there's less work. So solving for Vmax is not too hard. We just got to divide by m and square root. I think we actually have this expression from earlier. And yeah, let's finish it off. (85), we got about 1.5 squared, and the mass is 3 kilograms. So let's calculate this. So 85 times 2.25 divided by 3. Don't forget the square root. So pretty near 8 meters per second, which makes sense. A little bit faster. It should be faster than the speed from the previous question. So just a second example using conservation of energy. That's what you guys should be expected to do, is apply conservation of energy to mass on a spring. And this diagram really encapsulates those key ideas. At max stretch or compression, the stored potential energy is a maximum and the EK is 0. But when there's no stretch and the speed is a maximum, EK is maxed out, spring energy is 0. One last quick thing to talk about is damped harmonic motion. So, we've been neglecting friction in our problems, but in reality, you do have friction, and in a lot of things, you actually want friction because, I use the example here: when you step onto a bathroom scale, you don't want the little spring to constantly be going back and forth and back and forth. You want it to settle so you can see what your weight is, right? Same thing with maybe a bridge that's maybe perturbed a little bit due to the wind. We don't want our bridge to constantly be moving back and forth. We like, if there's a perturbation, we'd like it to settle quickly, right? So this settling down is called damping. And this leads us to a definition of damped harmonic motion. So it's periodic or vibratory motion in which the amplitude of vibration and energy decrease over time. So I believe I have a visual of that here. Yes. So over time, we've got the displacement of, say, a mass on a spring. And you can just imagine that if a spring on a mass on a spring is just going back and forth, that eventually friction is just going to settle it down and the amplitude decreases over time. That amplitude decreases exponentially. And so your displacement kind of looks like this. For those of you who have taken some high-level functions courses, and this is not need to know, but I can kind of show you the equations that govern simple harmonic motion. For simple harmonic motion, so no friction, no damping, the displacement or the stretch on the spring would kind of look like, it'd be like if there's no damping, then the amplitude just keeps going up and down, same amplitude, and you get a periodic or a trigonometric function. And so you would have something that looks like this. You would have the amplitude times the sine or cosine of, I say omega, so this is information about the period / frequency. And A gives you information about the amplitude. And you can completely model a mass on a spring using a function like this. In the case of damped simple harmonic motion, it looks similar. You have an initial amplitude, and you still have that periodic motion, but to account for the decreasing amplitude, you'd have some kind of decaying exponential function. And so if you don't know what this means, that's okay. It might be a bit above the last math course you did. But this gamma that I have here is a damping factor. So it tells you like maybe how much friction is present in the system or something, which tells you how quickly the mass on a spring will settle. So that's just some interesting taking it a little bit further. Because in reality, simple harmonic motion never really happens because we always have some kind of friction or energy lost in a system. All right, what's coming next? So we are going to take a pause at looking at energy concepts. So we've taken our work in energy concepts and tied in spring energy, looking at simple harmonic motion. We're now going to talk about momentum and impulse. Those, you might have heard momentum and use that term yourself a lot before, but you don't really look at it in the grade 11 course. We're going to define momentum, work with it, talk about what impulse is, make some connections to Newton's second law, and then a really fun part of the course, we're going to tie energy back in and use momentum and energy to analyze collisions, both one-dimensional collisions and collisions in 2 dimensions. It's going to be a lot of fun. And so until then, guys, hope you're staying well. Have a great day, and we'll see you soon.